So what we're going to do is we're going to use the Darcy-Weisbach equation and a Darcy friction factor approximation to calculate either the required discharge pressure at the discharge flange of this pump to get a given flow rate, or if we've got a given flow rate, what the pressure drop's going to be along this line. More often than not, in my experience, you're interested in the discharge pressure required to achieve a given flow. So let's say you want to fill this tank with water. You probably want to specify your discharge pressure to achieve a given flow rate. So let's say you want to fill it in 10 minutes, and what do you need your flow rate to be? And hence, what do you need your discharge pressure to be here to achieve that flow rate? Now, we're going to assume that you've got a piping length of 12 meters, your line diameter's a 2-inch on the bore pipe. Total height difference is 5 meters. And just to jump back, that's based on the inner diameter that you can find on the internet. So for 2-inch pipes, what's the inner diameter of a 2-inch non-bore pipe? Pipe absolute roughness again. So this is something you can find online. This is for a stainless steel pipe. It's essentially the bumpiness of the pump inside, which is going to contribute to your frictional losses. K value of a 90-degree bend. Again, this is just illustrative for this problem, but in reality, you might have some T-junctions, valves that's got pressure drop through them. I've just assumed there's two 90-degree bends. So yeah. Fluid properties as well. So you're going to have a density of 1,000, a liquid viscosity of 0.01. Again, depending on the fluid, you can find these properties either online, or you can have some specialist fluid software or physical property software, which usually tells you things like this. But most of the stuff in here is either something you'd know from the design of your system or something that you can find out online. So in terms of the algebra that we're interested in, so the Darcy-Weisbach equation, as per Wikipedia, is essentially this here. Now, there's a little modification that we need to do to this to make it usable for what we want to do. Now, you can customize it in different ways, but the way that I'm going to customize it is by converting this velocity into a volumetric flow, because generally we work in volumetric or mass flow. If we convert it to volumetric flow, it's reasonably easy to then go to mass flow, but we'll just do it for volumetric flow in this instance. Another thing as well is that this is an incomplete form of the Darcy-Weisbach equation. You can extend it to include K values, so that's what we're going to do. So first of all, we'll just extend it to include K values, and then we'll start working on turning this into volumetric flow. So first of all, to convert it into K values, essentially we group the density and velocity terms together. I'm going to keep the factor of a half with them as well. So rho v squared over 2. And then we're going to expand some brackets. And we're also actually neglected to do this on this side. We're going to move that L onto the other side as we do this. So essentially what we end up with is something that looks like this. So you've got your friction factor, and essentially the two terms that sit within these brackets can be split into frictional losses in the pipe and then fittings losses. So the sum of your K values. Now, again, these two terms inside are dimensionless. So essentially what happens is you get a multiple of a velocity head, and you would refer to this term as your velocity head. So that's the first thing to consider. Now, what I'm going to do, actually, I just realized I'm just going to make consistent with the rest of what I've done, I'm just going to turn that d into a lowercase d, which isn't massively important, but we're being proper, lowercase d. So first of all, we've got to turn this into volume terms. So the volumetric flow in a pipe is defined as the velocity in meters per second times by the cross-sectional area. So meters per second times meters squared gives you meters cubed per second. Now we can rearrange that to give us velocity is equal to Q divided by A. And then again, if we have V squared, which is what we've got in the equation over here, we get Q squared over A squared. Now again, we don't tend to work in areas of pipes, we tend to work in inner diameters, so we can actually amend that to say that the area is equal to pi d squared divided by 4. So again, if we've got A squared, we can say that we've got pi squared d to the 4 over 16. Now we can substitute this into, not this, rather this one, which will give us something to the effect of v squared is equal to q squared, which is our volumetric flow rate again, divided by a squared, so pi squared, d to the 4, and then you've got your 16 on top, like that. So we can substitute this in to this, and essentially what we end up with is rho times q squared, 16 at the front, divided by 2 times pi squared times by d to the power of 4. And then we've got all of that times by FD, LD plus the sum of the K values. Now, again, you can actually cancel these out to give you 8 and 1. And what you should end up with, I'll keep this neat, is 8 times rho times q squared divided by pi squared times by d to the power of 4. And then again, you've got your friction factor divided by, times by L over D plus the sum of your K values. Okay, now that's essentially the first stage of the calculations there. Just amending the algebra of the Darcy-Weisbach equation to a more usable form. So you can see here we've actually got in terms of pipe inner diameter, which is much easier to use, and we've got it in terms of volumetric flow rate, which again is generally the units we work in. We don't tend to work in units of velocity in pipes. So that's all good. Now, another thing that we need to mention, we need to look at, is essentially how we get this friction factor. Now, if we assume that the flow in the pipe is turbulent, which generally it will be for lower viscosity fluids, we need a way to approximate this. Now, for laminar flow, it's generally pretty straightforward. There's an approximation that you can do for laminar flow, which is essentially just 64 divided by the Reynolds number. That's a lot easier to deal with. However, you can, for turbulent flow, use different approximations. Now, there's all sorts. There's the Colbert-Wright equation. That's generally considered the best one to use. The problem with this is that it's called an implicit equation, in that you have to solve it iteratively. Now, we're probably going to have to solve this system iteratively anyway. So adding another layer of iteration required to solve it just complicates the whole situation. So what we're going to do is we're actually going to use an implicit approximation of the Colbert-Wright equation called Serghides solution. I think I pronounced that correctly. So, Serghides solution, if we get rid of this, we found on Wikipedia. So if we just drop that in there, so you can see that this is it's an approximation for the Darcy friction factor. So 1 over the square root of the friction factor is this lumped parameter A minus B minus A all squared over C minus 2B plus A. So again, these lumped parameters here, so these lumped terms are defined above. So again, this is an explicit form of the Darcy friction factor approximation, which makes it a lot easier to deal with than the implicit Colbert-Wright equation. And I think the accuracy for this is generally pretty close. A lot of specialist fluid flow software uses the Serghides solution, so it's good to go. It's used for turbulent flow, so it must be turbulent. So in terms of how we're going to set this up, so what I've done is I've put some equations here for the Serghides solution for the friction factor, and then I also put the pressure equation for the Darcy-Weisbach equation here, modified as we went through in the algebra section. So what I'm going to do is I'm just going to sort of talk you through how you build a spreadsheet to actually solve a problem like this one here. So we just jump back to the sketch. Again, we've got some parameters that we're working with, and we're going to solve. We're going to try and find the discharge pressure at this at the outlet of the pump to give a given flow in this line. So what we're going to do is we're going to start with some of the key parameters that we need to think about. So the way we're going to build it is we're going to take into account static head, obviously, source pressure. So the source pressure is essentially the discharge pressure of the pump. So we're going to say discharge pressure, P pump, and we're going to express this in bar gauge. Let's say as our first initial guess, it's 1 bar gauge. Okay. Now for this, I'm going to work in SI units. So I'm going to convert everything to SI units. Now, sometimes it's more convenient to work in non-SI units like bar, for example, just because they're easy to write down. So 1 bar is 10 to the 5 pascals. So it's a lot easier to write down 1 rather than 1 times 10 to the 5 or 100,000. So I'm just going to do that. Now, in terms of the static head, at source, so I guess you can call that, static head source, we're going to say there's no meters of static head. Okay, so there's we're taking that as our dating. And again, we want to convert that into pascals. So you need to multiply the height by density, and you need to multiply it by gravitational acceleration, which we haven't yet got. So we're going to add those down later on. Now, first of all, we're just going to say total source pressure, P1, and that's going to be equal to the pressure from the pump plus the static head. Again, that's going to be Pascal. That's going to be pascals. Now, we also need to know the destination pressure. Destination pressure, so where the pump is discharging to, what's the pressure in the system. We're going to assume that it's atmospheric. So we just copy and paste this down there. We're going to change this to 0 bar gauge. So it's equal to, I don't know why it's doing that, but we can just, okay. So 0 Pascal. Static heads. So destination static head. I'm going to say that's again equal to, what was it, 5 meters on the sketch? Yep, 5 meters. So it's 5 meters. Again, we are going to convert that into Pascal gauge at some point. We'll call this total destination pressure. That's P2. And again, that's going to be the sum of the static head plus the sum of the destination pressure. And again, it's going to be in units of Pascal. Now, it doesn't need to be Pascal gauge. It's not differential pressure. So what we now need to do is we need to work out the pressure difference, or delta P you can call it, and that's essentially the difference between the source and the destination. Again, so pascals. Now to start filling in the source static head and the destination static head, we need to write down the liquid density. Rho, and again, if you recall from page 1, we know that it's 1,000. And that's kilograms per cubic meter. So what we can do now is we can actually fill these numbers in. So we can say it's going to be equal to rho, which is the density here, times by 9.81, which is gravity, times by the height, which is this term here. Now I'm just going to fix this term, so I can just copy and paste this straight there. So there's no static head there, that's fine. And there's a bit of static head here because it's 5 meters above the datum, that's fine. What else are we going to do now? So I'm going to put in the inner diameter of the pipe. And I think I'm just going to set that equal to this here. So we've got the inner diameter of the pipe. Now, what I'm going to do, so I'm going to use this later on, is I'm going to calculate the cross-sectional area of the pipe. Now, first of all, I'm just going to convert this into SI units. So millimeters, 2 meters, divided by 1,000. And then I'm going to do, that's equal to 0.25 times pi times by the diameter squared. So that's just your general cross-sectional area of a pipe or a circle. Then what I'm going to do is I'm just going to get all the length values, sort of K values. So the length, again, I'm just going to set equal to whatever's on here, 12 meters, let's call it. And there. Sum of K values. Now you'll notice that I did the number for a single bend. We've got 2 bends here. So I'm going to make that 2. Again, this is dimensionless. Now, what we're going to do next is I'm just going to jump back and make everything that's an input yellow. And everything that is the calculation green. just to make it obvious, make it clear what's what. So again, this is a calculation, so we can make that green, we'll make it this color green. Calculation. This is generally a good idea for a lot of things because it means it's a lot easier to see what you've defined and easier to see what you've calculated. So this is sort of the core Darcy-Weisbach equation. We're getting everything together here. So you'll notice we've got density. We've not got flow yet, which we'll get to in a second. We've got diameter. We've not got friction factor. We do have length. Again, diameter. We do have the K value. So let's add in the volumetric flow. Okay, now this is something we're going to solve for. So let's just call it 1. Okay, and that's going to be in units of meters cubed per second. Now, it's sometimes probably more useful to have it as meters cubed per hour. So we're just going to times that by 3,600. Again, that's going to be something that we're going to iterate for. So I'm just going to call that blue. So now what we need to do is we need to find out what the friction factor is. Now, this can get a bit complicated. So what I've done is I've separated it out here. And we're going to start looking at all the terms that belong to the Serghides solution. Okay, so we've got to calculate each of these lumped terms here. So first of all, I'm just going to define what the absolute roughness is. So again, that is actually on the first page again, it's absolute roughness. Now, again, I'm just going to set that equal to whatever's on the first page, absolute roughness. Now, you'll notice that there's an E over D term. Now, this is actually termed the relative roughness. And I'm going to do this just to make life a bit easier for me later on. And essentially, that's defined as the absolute roughness divided by the pipe inner diameter. Again, this is in millimeters. This is dimensionless because millimeters divided by millimeters is dimensionless, as you can see. What else we have? We've got the Reynolds number. Okay, so for Reynolds number, we will need viscosity. So we can do that on this page, viscosity, and that's going to be equal to. So I've actually put it in centipoise here, but I'm going to convert that into SI units, which is going to be Pascal seconds. So that's CP, but to get it into Pascal seconds, we divide by 1,000, I believe. Yeah, divide by 1,000 Pascal seconds. And then we can calculate Reynolds number. And we do that by doing the density multiplied by the velocity, which I've just realized I haven't done yet. So I'm just going to go here and go velocity, which is going to be the volumetric flow rate divided by the cross-sectional area. That's meters per second. And again, this will look a bit high, but that's because this is just a first guess. So this isn't actually what the velocity is going to be. I mean, well, this is what the velocity would be if you did have a 2-inch pipe at 1 meters cubed per second, but 1 meters cubed per second is quite a big flow. So that's just not realistic at the moment. So for Reynolds number, we need the density multiplied by the velocity multiplied by the inner diameter, and then we need to divide by the viscosity. And that gives us our dimensionless Reynolds number. Now, another thing I'm going to do here, just to make life a little bit easier, is I'm actually going to define a few terms. I'm actually going to lump this together. So you'll notice it actually appears in all 3 of the lumped terms. So E over D divided by 3.7. So if I actually do that, E over D divided by 3.7. And this doesn't look massively neat, but you will see how this helps us equal to the relative roughness, which is E over D divided by 3.7. Again, that's dimensionless because it's inside a log. Now, what I'm also going to do is I'm going to define 1 over the Reynolds number, and you'll see again how this helps us later on, 1 over Reynolds number. And then I'm going to start defining each of the lumped parameters A, B, and C. So they all start with minus 2 times by log 10 of E over D divided by 3.7 plus 12 over Reynolds number. Now you can do this as 12 times by 1 over the Reynolds number. 12 times by 1 over the Reynolds number. As easy as that. Now I'm going to fix that one just to make it easy when I copy it down. This one is going to be wrong straight away, but I'm going to amend it. So you've still got the E over D divided by 3.7 as your first term, plus 2.51 times A over your Reynolds number. So again, I'm just going to do 2.51 times by A, which is this one, divided by your Reynolds number, or times by 1 over your Reynolds number. They all come out very similar, these is one thing I've noticed. C, again, C is very similar, in fact, to A. So I'm just going to fix all the terms in there. And you can do that on your keyboard by pressing F4 as a shortcut. And I'm going to copy this down. I'm just going to amend this because this needs to go to B. So you'll notice that C is the same thing, minus 2 times log 10, minus 2 times log 10 of K16, which is E over D over 3.7, plus 2.51 times K23, which is B, multiplied by 1 over the Reynolds number, okay, or divided by the Reynolds number, as it's in here. Now we put all those together to give us 1 over the square root of FD, like that. And that's equal to A, subtract. Now I'm going to do brackets there over brackets there. So I'll just, this is a little trick I like to do with Excel when you're doing complicated formulas, just try and make it easier to write stuff in. So you've got B minus A, which is B minus A, and then that's all squared, divided by C minus 2 times B, plus A. I'm just matching this. That's 1 over the square root of FD. So we can actually change it into the square root of FD. Now you could do this all in one step, but I'm just going to do it in a couple steps just to keep things simple. And then that's the square root. So to get FD, we need to square that. And the result should be a number that is around, I mean, you can look on Moody diagrams and find what ranges friction factors tend to be in, but that's a reasonable FD. You tend not to get it above 0.1, 0.2. It's generally 0.0 something. So what we can do now is we can actually look back at our equation up here, and we can try and start building the iterative part of this calculation. So essentially, the way that you would do this iteratively is you would essentially replace this equal sign with a negative, with a minus sign, and then set it equal to 0. This is essentially how we're going to solve it with the computer. So if I just do equals 0 like that, that's essentially what we're going to be writing into the program, because we're going to struggle to solve this analytically because we've got a diameter here, we've got diameters inside the FD. Inside the FD, we've got Reynolds number, which contains velocity, and velocity is related to Q. It just gets very messy. So what we're going to do is we're just going to do it like this, iteratively instead. I'm just going to pull this down here. And then essentially what I'm going to do is I'm going to call this the left-hand side of the equation. So you can call it LHS. And that's essentially just going to be equal to your pressure difference, which is that, what we defined earlier. Now the right-hand side of your equation, I'm going to define as this. I know strictly it's not the right-hand side of the equation anymore, but we're going to define it as that. This gets a little bit more complicated again, but we're going to try and build this out. So we've got the first bit, so we're going to do 8 over that times by something there. So we've got the 8 multiplied by the density, multiplied by the volumetric flow squared, and that's all divided by, now that should be pi squared, I've just realised. That should be pi squared. I'm not just going to shout at me for that. All times by pi squared times by the inner diameter to the power of 4. That is correct, that part, the diameter to the power of 4. And then again, it's going to shout at me. I'm just going to put something in there to keep it happy. That's going to be squared. So that's one thing I forgot earlier on. I might have just forgotten to write it in here, but that should be pi squared. So what's going to happen next is we're just going to finish this off. So 8 times by density times by the volumetric flow squared, divided by pi squared, times by d to the power 4, times by, now I've put 1 as a placeholder. We actually want friction factor times by the fraction that is L over D, so length over your inner diameter, and I'm going to plus the K values, the sum of the K values on as well. Now, what we want to happen is the left-hand side to the right-hand side needs to equal 0. So we can call this field here the error, essentially, if you want to call it that. So we're just going to define that as this minus that. Now, solve this kind of depends what you want to achieve. So if you want to find out what flow you get when you set your discharge pressure in your pump to, let's say, 1 bar, what you can do is you can go into your goal seek and you can say set this value to 0 by changing the volumetric flow rate. And then that will tell you if you have this discharge pressure with the given system characteristics, your static head, your viscosity, density, inner diameter of this, and so on, then you will get this amount of flow. Now you can use it in the reverse as well, which is often more desirable to determine what pressure you need from your pump to give a given flow. So let's say, for example, instead of me wanting to know what flow I get when I have 1 bar of discharge pressure on my pump, let's say I want to specify my pump and say, well, I actually want to get 10 meters cubed an hour out of this. So first of all, this is, and you can build the Excel sheet differently to make this easy to do. But what I'm going to do is I'm going to say, let me set my meters cubed per hour to a value of 10 by changing my meters cubed per second. So this is just to make my life a bit easier. So I need to aim for 0.002 meters cubed per second. Okay. Now again, this will give me an error because the energy balance doesn't really work the way that the system currently has the numbers. So what I'm going to do is I'm actually going to change it and say goal seek this as before to 0, but instead of by changing the volumetric flow rate, I'm going to change the pump discharge pressure. So what this should do now is this should tell me, well, if I want 10 meters cubed an hour flow, then I need to specify pump with this much discharge pressure. Now, of course, you're going to go to 2 decimal places rather than any more than that. So this is essentially saying, well, if I've got a system like this, to get 10 meters cubed an hour into this tank, I need to specify that the pump has a discharge pressure of 0.52 bar.